Hey, we are going to continue on with hypothesis testing, but it's going to be a bit different. We've been using quantitative data. We've done hypothesis tests for proportions, for two proportions. We've done hypothesis tests for means, two means, the difference of means, and all that we used quantitative data. So what happens if you have categorical data? Well, what we're going to do is we're going to do chi-square tests. And it looks like here it looks like it says x squared, but what it really is the Greek letter chi that looks like an x, and that's what this says, chi. It's not chai, it's chi. And today we're going to talk about the goodness of fit test associated with the chi-squared. We'll do a couple different chi-squareds in class together on Tuesday. So if you look at page 673, this is where I got my information from. What I have here is the 12 months, and we just ordered them from 1 to 12 instead of January to December. And in this column, we have counts. Okay, so we have 12 categories. Each of them are the different months, and then we have some counts. So what the question or the problem is posing is saying that there's a belief that the month you're born in has some effect on your ability to become a professional athlete, specifically a professional baseball player. So to test that, 1,478 baseball players were picked from 1975 to present, and their birth month was recorded. And so what these numbers represent are the number of baseball players out of that total that were born in each month. And in this column, we have the percentage of births in the United States per month. Not associated with baseball players, but just associated in general with people being born in that month. And these percentages all add up to 100. So this is 8% of the total births are in January, 7 in February, 8% in March, so on and so forth. So what we want to do is we want to see does the percentage of baseball players born in each month differ from the national birth percentages. So these are distributions. This is a distribution of all the people born in the United States over 12 months. So we want to see if the distribution of baseball players is different from that, what we would see in general from the general population. So this is categorical data because we've just counted the number of people who belong in a category. And what we'd like to do is calculate this last column, which is called the expected number. So we're going to perform some sort of hypothesis test, and our hypothesis is always going to be that our observed thing is the same as what we would expect it to be. So if 8% of people are born in January, and we have 1,478 people sampled, we would expect that 8% of that 1,478 would be born in January. So we'd multiply 8% times 1,478, and we would expect 118.24 people. And we'll leave the decimal. This is a bit theoretical. And so we can calculate this column by doing that for every percentage. So 7% times 1,478. Our 8% are all going to be the same, so on and so forth, and we get this column of expected values. So if in January 8% of people are born, if we sample 1,478 of them, we would expect 118.24 to have been born in January. This column, the count of baseball players, is associated with what we actually observed when sampling 1,478 Major League Baseball players. So let's talk about doing a hypothesis test for categorical data when we're doing a goodness of fit. So what we're trying to see is, does the distribution from our sample fit the distribution that we expect from what we know? So our data must be counts. We talked about them being counts of baseball players born in each month. The counts need to be independent and random. That is a thing that needs to always happen. So each baseball player's birth month is independent and random. And the expected values should be at least 5. So if I go back In all of these cells in this column, the number needs to be 5 or greater. And for all of them, it's much, much bigger than 5. So we've met all of our assumptions and conditions. So it's a little bit different from the NP and the NQ. It's different from means, where you have to look at a normal probability plot. Here we're looking to see that all the expected values are bigger or equal to 5. Our hypotheses are going to be a bit different, and these are also on page 676, if that's easier to read for you. Before, we're used to saying that P, some proportion, is equal to, greater than, or less than. For means, we're talking about mu, the mean of something, being equal to. Here we just sort of have to state what we're talking about. So our null hypothesis is that the distribution of birth months for Major League Baseball players is the same as the regular population. So that's why we did the expected values. The alternative would be that there's some difference. So the distribution of birth months for our Major League Baseball players is different from the rest of the population. So it's sort of like an equals to and a not equals to. So we've been calculating test statistics for population proportions. We calculated Z's. For means, we calculated T's. And here we're going to calculate chi-squared values. And we could actually calculate a chi-squared value by hand, but it takes quite a bit of work. This means to sum. And we would take the observed value. So, for example, for each of these categories, each month, we would take the observed value, subtract the expected number, square that value, and divide it again by the expected number. And then we would do the same thing for the next category and the next category. And we would add all of those values together. The reason that we do a squared is so that we can get rid of any negatives, so it doesn't throw off our value. And what we would get is called a chi-square statistic. Chi-square is kind of like means, and we have a degrees of freedom. So before, with means, the degrees of freedom were the number of samples minus 1. Here it's the number of categories minus 1. So we have 12 months, 12 categories, we subtract 1 and get 11 degrees of freedom. So naturally, there is a function on your calculator that can do this for you, so you don't have to go through that painstaking calculation by hand. And so I'll show you that. In one list, in our calculator, we would put the observed values, and in one list, we'll put the expected values that we calculated. I can also show you how to get the list of expected values without having to calculate each of them individually. We can talk about that in class. Then we're going to go to our stat and tests, and we're going to select this. It looks like x squared, but it's chi-squared, goodness of fit test. We'll tell it which list is our observed values, which list is our expected, and what our degrees of freedom are. And then we can calculate, and it'll actually give us the chi-squared statistic that you could calculate by hand. That's 26.48. And it'll give us a p-value like we're used to getting. And we're going to compare that p-value again to an alpha value, which is probably going to be 0.05. So we would say the probability of getting a chi-squared test statistic with the degrees of freedom of 11 greater than or equal to 26.48. We're doing greater than or equal to because we're trying to see if there are more people in certain months that can play Major League Baseball, is 0.0055. 0.0055 compared to a alpha level of 0.05 tells us to reject the null hypothesis. This is a really, really small probability. That means that it's very unlikely to have sampled the baseball players and got a distribution of their birth months that we got if it's the same as the national distribution. So it's very unlikely. So it's looking like there is a difference between our baseball players and the normal population. So our chi-squared curve is going to look different than a normal distribution. It's skewed to the right. There's a different curve for every number of degrees of freedom. There's a lot of theory that can go into it, but it would look like this, something like this. Because it's a squared value, all our values on the axis are squared. It starts at 0. There's not going to be any negative values. And so the higher your chi-squared value, the less area under the curve, the less probability of something happening. That's like our normal situation, though. And so we can draw a conclusion the same way we have been. We would say with a significance level of 0.5 or 0.05 and a p-value of 0.0055, there's evidence that the birth months of Major League Baseball players have a different distribution from the rest of us. So the calculations are a little bit different. You got to do a couple extra things. You got to calculate the expected value column. But then your decisions that you make to reject or fail to reject and your conclusions that you draw are going to be very similar to what we've been doing. So we can go over this in class. We'll do some practice, and we're going to do some different chi-square tests when we see each other.